All right, so this is conservation of momentum combined with conservation of energy. Now, what we have is bullet. I'm calling the bullet M1. It collides with this block that's hanging from two ropes here. So that's the collision part. Now, when you have a collision, you can use conservation of momentum. You cannot use conservation of energy unless the problem specifically tells you that energy is conserved. But look, the bullet has kinetic energy before the collision. There's going to be kinetic energy after the collision, but these are not equal because where does a lot of the energy go? Heat. It goes into heat energy. If you stuck your finger in this bullet hole, what would you notice about that bullet hole? It's hot, dude. It'd be really hot, okay? So you cannot use conservation of energy in the collision, but you can use conservation of momentum. All right, so conservation of momentum, M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. So all that's saying is total initial momentum equals total final momentum. If you look at this block here, M2, what's the initial velocity of the block? It's just 0, so you can cross this part out. So this is going to shorten things up here, right? The block has 0 momentum before the collision, so this is going to simplify things a little bit. So I'm going to take this and just scoot this over here. You see that? Boom, like that. All right, now what the problem wants us to find, what we're trying to find here is the initial velocity of the bullet. So what we'll do here is divide both sides by M1. Then over here, the M1s cancel, right? So let's just get rid of those M1s. So the initial velocity of the bullet is going to equal this. And we have everything here except one thing. What are we missing? V2 final, which is the final velocity of the block. Now, what do I mean by final velocity of the block? Do I mean up here? I mean like when the bullet is coming out of the block right here. Like, so the bullet goes, it rips a hole through the block. As the bullet comes out of the block is going to have a velocity, right? So to figure that out, we can use conservation of energy. So this is post-collision, because I know what some of you are thinking. You're thinking, Spaldo, you just said you can't use conservation of energy, which is true, but this is post-collision. Can we use conservation of energy after the collision? Yeah, because we're done losing energy, right? So post-collision, focusing on the block. What type of energy does the block have right after the collision? Kinetic, and then that kinetic goes to potential because it comes above the 0 point. So this line right here, this line is the 0 point right there. Okay, so we got our equations here. So we're going to say kinetic initial equals potential final. So you go 1/2 mv squared equals mgh. The m's cancel, which makes it nice. So v is square root 2gh. So that's 2 times 9.8. I'm leaving the units off. Bad physics teacher. I'm almost out of room. The h is right here, 0.12. Okay? So this velocity comes out as 1.53, and that is the final velocity of the block after the collision. You're so smart now. You guys are super. You guys get this? Yeah. You're smart. I told you. You're smart. Okay, now I'm going to shrink this down like that. Put that up here. What? Boom. Okay, now M1, 0.007. That's the mass of the bullet. V1 final is this right here. It's the bullet after the collision. 200 plus, okay, M2 is the block, 1.5. And then V2 final, we just solved for that. That's 1.53. Okay, and then divide all this by the mass of the bullet, and we get 528 meters per second. This is how they used to figure out velocity of fast objects like bullets and stuff. They'd fire it into a hanging block. If you know the mass of the block and how high it swings and the mass of the bullet, you could figure out what the velocity of the bullet must have been. All right, any questions on this? So this is what the lab will be on. All right.